Welcome to this tutorial on setting up a power measurement for a two-photon microscope system. This video is brought to you by the Quality Assessment and Reproducibility for Instruments and Images in Light Microscopy Working Group 1. The information provided in this video is for educational purposes only. The Quality Assessment and Reproducibility for Instruments and Images in Light Microscopy, QUAREP-LiMi, working groups, along with any associated individuals or organizations, are not responsible for any damage to equipment, injury, or harm to individuals resulting from the use or misuse of the procedures demonstrated. Viewers are advised to follow all relevant safety guidelines, consult with their local safety officers, and adhere to the equipment manufacturer's instructions before performing any measurements or handling lasers. Use of this video content is at your own risk. Hazardous, visible, or invisible radiation from two-photon lasers can cause permanent damage to the retina, skin burns, and fire. Always follow proper laser safety protocols for your equipment and situation. Be aware of any reflectance of laser light caused by objects immersed into the laser light path. Before you take any measurements, it is important to familiarize yourself with all laser safety rules and requirements to avoid eye and skin exposure to scattered or direct radiation. Please refer to the documentation provided by the manufacturer for additional warnings and preventive protective equipment (PPE) requirements, for example, laser safety goggles. Always consult with your local laser safety officer or radiation safety officer and refer to your laboratory safety documentation for more information. You can also consult your laser safety standards ANSI Z136 in North America, SUVA 66049D in Europe, and BSEN 6825-1 in the UK. Additionally, laser safety standards and regulations are covered by IEC 68251, and LED eye safety standards and regulations are covered by IEC 62471 in Europe. The components required for this measurement include a power sensor to measure the relative peak power of two-photon lasers, a power meter console, a microscope, a two-photon laser, and optional software for remote control and monitoring. In this video, we demonstrate the setup using an upright Leica TCS SP8 MP multiphoton microscope equipped with a Coherent Chameleon Ultra 2T Sapphire femtosecond laser, tunable from 680 to 1080 nanometers. The power sensor featured is the Thorlabs Microscope Slide Peak Power Sensor for two-photon lasers, NS170C, paired with the PM100D Power Meter Console. Links to both the power sensor and power meter console are provided in the description below. We also use the Optical Power Monitor OPM software, which is fully compatible with the power meter console and interface. This software enables remote control and monitoring of up to 8 power and energy meters simultaneously. The NS170C Microscope Slide Peak Intensity Sensor is specifically designed to measure the relative peak power of femtosecond lasers at the focal point of two-photon microscopes. It contains a 30 millimeters thick beta-barium borate (BBO) crystal that converts near-infrared femtosecond pulses into visible light through second harmonic generation (SHG). Optical filters beneath the BBO crystal block NIR light, allowing only the visible second harmonic light to reach the photodiode. The sensor works based on the peak intensity and polarization of the laser pulses. Positioned at the focus plane, it captures these signals precisely. The sensor is compatible with standard microscope stages and works with upright and inverted setups. It detects SHG light at signal levels in the range of hundreds of microwatts, milliwatts, with a high signal-to-noise ratio of around 10,000:1. The sensor can handle up to 350 milliwatts of average power and is compatible with dry water and oil immersion objectives. Now, let's walk through a step-by-step demonstration of how to perform a power measurement for a two-photon microscope system. The first step is to securely position the NS170C two-photon sensor on the microscope sample stage, aligning it directly beneath the objective. Ensure the optimal longitudinal position is less than 30 millimeters in depth with high numerical aperture (NA) illumination. In this demonstration, we use a 10x air objective. To minimize the risk of component damage, begin with the sensor positioned below the focus, and gradually raise it until it comes into focus. Step 2. Power on the microscope following the standard procedure, ensuring that the settings match those used in the experiment. Step 3. Powering on the laser and tuning to the correct wavelength. Turn on the two-photon laser and tune it to the desired wavelength. Ensure that the laser has been warmed up and stabilized for at least 20 minutes before starting any measurements. For optimal performance, consider warming up the laser overnight by powering it on the evening before and keeping it in standby mode. Finally, verify the output power and confirm that the laser is properly mode locked to ensure accurate operation. Step 4. Connecting the power meter console and launching the OPM software. The next step is to connect the NS170C sensor to the power meter console and then connect the console to the operating computer. Once all connections are secure, launch the optical power monitor OPM software. Upon initialization, the meter may report a small non-zero power reading, such as 0.7 microwatt, displayed on the screen. This reading indicates the baseline noise or ambient power detected by the sensor. Step 5. Calibrating the power sensor. To calibrate the power sensor, first confirm that the wavelength setting in the software matches the laser's wavelength. Then, disable the auto range feature, cover the sensor to block any ambient light, and click the Zero Adjustment button. This process eliminates background noise and ensures balanced and accurate readings. Step 6. Optimizing the focal position for SHG signal detection. To minimize the risk of damaging components, begin with the sensor positioned below the focal point and gradually move it upward into focus. Since the BBO crystal is only 30 micrometers thick, any power changes during focal position optimization will manifest as a brief flash in the SHG signal. Carefully adjust the objective position to avoid missing this brief signal change, which will be displayed on both the power meter console and the software interface. Turn off the auto range feature to prevent it from obscuring these rapid power fluctuations. Manually setting the power range allows the meter to climb incrementally to its range maximum, offering clearer and more intuitive feedback. Once the flash is detected, increase the power meter's range to fine-tune and accurately optimize the focal position. If you move past the focal plane, the SHG signal will suddenly drop, clearly indicating the location of the focal plane. Adjusting the BBO crystal angle for optimal SHG signal. Once the focal position is established, the next step is to adjust the BBO crystal angle to maximize the second harmonic signal. The orientation of the BBO crystal can be finely tuned using the exposed knurled wheel, enabling precise optimization of the second harmonic generation SHG process. If the polarization state of the NIR laser relative to the NS170C sensor is known, align the knurled wheel so that the angle indicator dash mark is parallel to the laser polarization. If the polarization state is unknown, adjust the BBO crystal orientation by rotating the knurled wheel while continuously monitoring the SHG signal on the power meter. The optimal crystal position is achieved when the SHG signal is maximized. Step 8. Recording. The final step is recording. Click the Settings button under the Graph tab to select both live and recording settings. In this video, we chose a 20-second recording duration. To start, click the Record button at the top of the display window. Once the recording is complete, a graph will appear on the screen with time displayed on the x-axis and average power shown on the y-axis. To establish long-term system performance data or determine global maximum SHG readings, it is recommended to follow an optimized routine. For instance, use a level when mounting the sensor to ensure consistent orientation. Before starting a new monitoring session, configure the settings, including file name, file path, file size, and saving interval. Once the setup is complete, click the Start Logging button. When the monitoring is finished, the results will be displayed on the screen as a logging chart graph. If the system's pulse duration is adjustable, fine-tune the GDD of the pulse compressor or the laser's built-in GDD precompensation while monitoring the SHG signal on the power meter. The optimal pulse duration is reached when the SHG signal is maximized. Note, this process is not demonstrated in this video. The information provided in this video is for educational purposes only. The quality assessment and reproducibility for instruments and images in light microscopy, QUAREP-LiMi working groups, along with any associated individuals or organizations, are not responsible for any damage to equipment, injury, or harm to individuals resulting from the use or misuse of the procedures demonstrated. Viewers are advised to follow all relevant safety guidelines, consult with their local safety officers, and adhere to the equipment manufacturer's instructions before performing any measurements or handling lasers. Use of this video content is at your own risk. Please refer to the protocol developed by the Quality Assessment and Reproducibility for Instruments and Images in Light Microscopy Working Group 1, Illumination Power, Stability, and Linearity Measurements for Confocal, Wide-Field, and Multiphoton Microscopies. For more tutorial videos, please click the subscribe button for QUAREP-LiMi.